Hello students, continuing with the proof of autocorrelation, we will take the second property and try to derive its proof. So second property I have written here, r x of 0 is equal to expectation of x square t. This is nothing but your second moment. It's called that second moment for the random process for x of t. So proof for the same by definition of autocorrelation function, we know that r of rx or r double x, one and same notation, x of tau is equal to expectation of x of t into x of t minus tau. Done. So put tau, this is by the mathematical definition of this, mathematical definition, or you can say quantitative definition. You have r x of tau equal to expectation of product of x of t into x of t minus tau. Put tau equal to 0 in the above equation, you will get r x of tau is equal to e x of t into e x of t minus 0, that's e x of t. So answer will be clear cut, e x square t. So this is r x of tau. Now this value, since this is an second moment function for the random process x of t, this will be always greater or equal to 0. Obviously this will be some positive value, so that's why I have written here that this should be greater or equal to 0. Done. So this is the proof for the second property. Now we will try to write down third property and try to derive its proof. So third property here is mod of rx of tau will be always less than or equal to rx of 0. That means maximum value of autocorrelation function should occur at tau equal to 0, and tau is always equal to the time difference between the two time intervals of the same random process in this autocorrelation function. Now I will try to prove the same. Now before proving the same, we will try to write down this Cauchy-Schwarz inequality. By this inequality, we can write expectation of x y whole square should be always less than or equal to individual expectation of x square into expectation of y square. Now we will put x equal to x of t and y equal to x of t minus tau. What you will get? Then I will get expectation of x of t into x of t minus tau whole square less than or equal to expectation of x square t into expectation of x square t minus tau Done. Now since expectation of x of t into x of t minus tau, by the definition of autocorrelation, this is nothing but your r of tau. So you can write this equal to r of tau whole square. This is always less than by this inequality, Cauchy-Schwarz inequality. We have written this. Then try to write x equal to x of t, y equal to x of t minus tau. Then put the value of x and y in the above equation inequality. Then try to write this. Now since this e expectation of x of t into x of t minus tau is nothing but your autocorrelation function, so I have written this r of tau ka whole square is always less than or equal to e x square t into e x square t. Why? Because since e x of t and variance as well as second moment, they are constant for a stationary process. They are constant for a stationary random process x of t. So I will write this like this: r of tau whole square is less than or equal to e x square t whole square. Why I have written this equal to this? Because this is a stationary process, so e x square t minus tau can be written as e x square t, because this is independent of time. This is not dependent of time. That is by the definition of stationary random process. So after taking this can be written also, because from the above second property this can be written as r x of 0 whole square. This is because from second property already defined above and proved also. So you can say r tau, that means autocorrelation function square, is always less than or equal to r x 0 whole square. That means autocorrelation function at 0 whole square. Now I will try to take, now taking square root on both sides, taking square root on both sides, what we will get? We will get r of tau, r of tau mod r of tau less than or equal to r of 0. Now since, why I have not written here mod? Because r of 0 is equal to expectation of x square t, and this is always positive. Expectation square, it's always greater or equal to 0, so this is always positive. So we have proved that the maximum value of autocorrelation function occurs at tau equal to 0. That means all other values of autocorrelation function other than tau equal to 0 will be less. That means maximum value will occur at tau equal to 0. Similarly, another property which I will just write and you will try to prove the same, that autocorrelation function of, that means autocorrelation function R of tau of a real stationary, why I have written real, because there can be also complex process, of a real stationary process x of tau is continuous at tau equal to 0. If this is continuous at tau equal to 0, then it must be continuous at every other point. This is one of the properties which you will try to see it.